Well, it's my great pleasure to host you here today. It has been a very interesting work to be able to gather such an interesting group of invited for the seminar we're just starting today. As most of you know, because most of the audience here is from our master program, this is our first lecture and first seminar in our Distinguished Innovators Lecture Seminar from the Master of Innovation at Catholic University. It is my great pleasure, really, to be able to introduce our first speaker during this term. And our guest is Professor Dava Newman. Dava, she's a professor of aeronautics and astronautics engineering and engineering systems at MIT. And she's the director of technology and policy program, and she's a McVicar faculty fellow. Dava, as all of you learn a little bit about it for the session that we had yesterday where we prepared this seminar, she's a very interesting person with multiple interests. And she got her bachelor degree at Notre Dame in aerospace engineering. And then she got 2 master degrees at MIT. One is in aeronautics and astronautics engineering, and another one in technology policy. And finally, she got her PhD at MIT in aeronautics, biomedical engineering. She's a professor in the Department of Aeronautics and Astronautics and Engineering Systems at MIT. And she's an affiliate faculty in the Harvard MIT Health Sciences and Technology program. She is also a McVicar faculty fellow, as I mentioned previously, and she's the director of the technology and policy program at MIT. And she also is the director of the MIT Portugal program at MIT. As I mentioned, it's my great honor to be hosting today our guest, Dava Newman, and I hope you enjoy very much her seminar, and we're looking forward as well after the following interaction of the seminar, so please give her a big applause.
Can you hear me? Yes. It's okay? Okay, testing. Excellent. Well, thank you so much for the invitation. It's okay in the back to hear? All right. Thank you for allowing me to speak in English as well. Tell me to slow down. I tend to speak quickly. I'll try to go slowly. Just like I have to buckle up my belt here. I'm trying to, maybe I just hold it. We'll move on. I think you know a little bit about my background. I heard you had homework to look at these things. So I can introduce my partner, better half, Guillermo Tratti, is here in the audience with me. So I thought that what we could talk about, if you allow me, I would like to introduce you to the field of bioastronautics. Human space flight. That's my passion, and I'd like to share a little bit of our research, talk about some innovation projects with you. And I have a pretty simple philosophy for all my teaching and research, and it's up there: to love, act, discover, and innovate. And hopefully you can still hear. Excellent. So we'll start our journey on Earth, and then we'll move to space, microgravity, take you to Mars, and we'll come full circle back to Earth. And I have a question for you and homework for you, because I know that we have a quite an extended discussion. And I know it's a really mixed audience, so speaking to all the engineers, but all the other designers and journalists and lawyers, what's the future of innovation? It's a great question. You're the experts, are 3 semesters into your program. I spend a lot of time thinking about what we call STEM education: science, technology, engineering, and math. But I've expanded it to STEAM because actually I think it's really important for us to include the arts. And so that's kind of a bit of my personal mission. As an engineer, we have not done a very good job. Actually, you might say we've done a pretty poor job at communicating our in our profession as professional engineers just how cool engineering is. Because what do? We try to solve the world's problems. We try to design and build things for the betterment of humanity. But there's a lot of data, at least in the US, that shows us that kids don't know what engineers do. And if you want to solve a problem, maybe you should grow up and be a doctor or a lawyer. But usually engineering, they don't know about it all. And they don't know that we're kind of the inventors, innovators, and again, kind of dedicated to solving some of humanity's large challenges. So that's just a little bit of my discussion to pose that as I go through my talk, and hopefully we'll come full circle. I wanted to highlight the work of a colleague and a student, a future faculty member at the Catholic, Julio Pertuz, and he's assessed industry-university relations and basically asked the question and helped answer it. Why do they go not so well? What's stopping us from having better industry-university relations? The follow-up question for his PhD work, it's a very tough problem. What about industry, university, and government relations? We call that the tripod. We all want very good collaborations and relations, but in our systems, kind of what prevents some of the innovation and some of these things. So that's the agenda for my talk for the next hour or less, and then we'll have questions. So again, starting with a bit of a, I don't know, provocative or questions for you, things to think about. When I think about innovation and the need for kind of radical or revolutionary, a different way to solve a problem, well, I go back and I have a couple heroes. I have more heroes than would fit on the slide, but I say, what are the commonalities? You know, what might be similar in terms of what we might call great thinkers, but also great doers? So I put Galileo and Picasso there for a couple examples. You can disagree with this, but I think perhaps that really innovative thinkers, they create, the creative genius is often in their generalities, not the real specific details. Their new ideas, they might illuminate a pathway towards a whole new way. They're really expanding knowledge, new way to look at things. They definitely inspire what we might call in engineering a step change, a great leap forward. You know, this is not incremental work, it's a great leap forward. And transformation of intuition. You know, we've been thinking about the problems, we've been thinking about them really hard. You know, what helps trigger us, and let's think about the problem in a new way. And bringing together people of different disciplines is about the best way that I know how to do that personally. So maybe creative paradigm shifts are simple, elegant, a little bit majestic perhaps, and the result of maybe a different way to think. I think that for sure we need an environment that really inspires, you know, creativity, imagination, and innovation. It's wonderful to be in this building. We just walked through, but it seems like a pretty inspirational, wonderful building in itself. So that's just some things to think about. We'll kind of finish the talk, and again, if you agree with me or disagree with me. I said I'm going to start on Earth. So some of our work here on Earth, I look at locomotion, musculoskeletal performance, trying to enhance performance. Sure, we look at locomotion devices. I think you've maybe been paying attention to the Olympics. So how does Oscar run? You know, with incredible musculature in his upper legs and then some springs for feet. He does not have a mechanical advantage over full-bodied people. All he does is get some elastic spring energy in there. We'll get to the aerospace part, but I tend to work in the field of aerospace, but really looking at humans and robotic cooperation. So actually my robot, this is a full-sized robot, actually 95th percentile male, or big person. There's Rudolf Opperman, actually a South African graduate student who worked with me. And you know, we're tracking motion, kinematic. We're looking at motion and driving the robots. So the robot is just essentially my surrogate astronaut, or my surrogate athlete, because I have very high precision optical encoders that I can measure the motion, but more importantly than that, I can actually measure the torque. So, you know, F equals ma, the torque, you know, how hard are we working for all the joints? It's 12 degrees of freedom robot. This is some other work by Mark Ray. Watch these little robots. If you can see these robots, a biped and a quadruped. Watch the biped. Oh, you're supposed to clap. If you're an engineer, this is a really hard problem. How gymnasts, again, back to how the gymnasts can do that, that's really hard physics. And so to make a robot do that with all the control algorithms and dynamic stability, it's easier for the quadruped because we get 4 legs to work with. It's harder for the biped. You know, so some fun, great work. And I don't know if this is on. Then to wake you up, even in the beginning of my talk, oh, I guess I have my sound off, but I'll put a little sound. Maybe I won't put the sound on, it's really loud. But again, inspired by nature, the point of this is I learn a lot from emus and ostriches, and we're trying to take some of these designs. This is a colleague that actually taught with Guy at the Rhode Island School of Design, and myself, Steve Copeland. He's able-bodied, but imagine you wanted the world's fastest, he calls it the Greyhound, the world's fastest cycle for someone that had paraplegia. So I don't have use of my leg muscles, but I guess he'll be a really good cyclist. So all the propulsion comes from his upper body, all the steering and control also comes from his arms, and he can use one arm or the double propulsion stroke of two arms. He's zooming around the Philadelphia subway in case you've ever been there. And we think it is. Steve's the main designer, worked with students to do the prototyping, and then we tested it at MIT in our wind tunnel and around the track with Boston Marathon athletes. But it couldn't be used in the Boston Marathon because it's illegal, because they have to be in an upright wheelchair, and this, it would be too fast, I guess. So. It's recumbent and you're down, so it couldn't actually be used for the Boston Marathon. But I think a beautiful design of designing for humans, and again, learning a lot, fun collaboration. I wanted to show you this work. We're trying to help folks walk. So in this case, it's a subject with a pathology known as drop foot. You might know someone who suffered from stroke, and typically if you've suffered from stroke, it's asymmetrical. So one good side and one bad side. Well, this is the work quite a while ago. Now, my graduate student, Joaquin Blaya. He's a Chilean American. So I wanted to highlight some of Joaquin's work. Again, we do a lot of musculoskeletal modeling. You've seen that. There's a bit of engineering analysis up there for those folks. What are we doing? Here's the subject. We're using a drop foot. The foot will slap down. You see the orthotic, and that's Joaquin there with the green shirt on. And so the foot will slip down. We put this, it's actively controlled. This is a linear elastic spring here, series actuator. His foot will slap down. It really hurts. That's called the slap foot. And then you don't have the musculature, so you'll drag the toe, and you usually can't walk. So we have a learning algorithm in there. It's adapting to him. He has it on. Unfortunately, he's tethered to our computers. So see how it's taking data from the good side, saying, I want the impaired side to be just as good. And I program in the angles, and he walks in. That was as fast as this gentleman had walked in years after his stroke, of course. But the sad part was he couldn't go home with it because he was tethered to our computers. It was actually 10 years ago. My colleague Hugh Hare at the Media Lab is actually, even a nicer version. This is orthotic to put on someone's leg, of course. But for amputees now, Hugh's invented, his company is called iWalk. And he's probably invented the best knees and ankles around, in my opinion. Joaquin, back to his story in innovation, entrepreneurship, he's finished his PhD. This was his master's work with me. He's finished his PhD between MIT and Harvard, and he has a Chilean startup. So he's kind of living between Chile and Boston, and it's e-health solutions. So his website's there. He's doing some really nice work in electronic health IT systems for Chile and the world, but the startup is based out of Chile. So what else are we doing to, again, kind of try to enhance performance, look at things? Well, we measure walking and running and jumping and you name it. With pretty expensive, we put a lot of sensors on people. This is a big motion capture system, in case you're familiar with the technology, 16 camera Vicon system, measuring motion, such as you see here. And then we do the engineering analyses, basically. These systems are very expensive, $200,000 or so. So most universities can't have them. Most medical doctors can't have them. What can we do about that? Well, we think we can get rid of those gold standard, and we just use these small little sensors. They're what we call IMUs, inertial measurement units, and they kind of came from the aerospace industry. They're pretty small, about as big as my watch right now. So even I have a smaller set than that. And we strap them on people, and we can still measure these motions and take a look. And that's what the data is plotted. The green data is the big fancy system.